Right. Today will be my last lecture before the exam. I thought about giving you another quiz today, but I didn't.
When is the exam?
The exam is on Friday, and it's student presentation on Wednesday. Right, folks?
Yeah.
Got a question, Jessica?
So, in one of my classes, I have a field trip on Friday.
Wah, wah. Do you want me to be honest or funny?
Well,
It's going to be hard to pass the class with that zero. Okay, that maybe doesn't seem so funny to you. Okay, come talk to me later.
okay.
Okay, so today I'm going to actually kind of review the telescopes once more. I found the slides that I thought I had put in, but obviously didn't, when I was talking about telescopes. And so I'm going to go over them some more. I ended last class period talking about this diagram. This diagram shows on the top the wavelength ranges where light can get through the atmosphere. And the notable things are that in this range right here, we call this the visible window, light can get through. And so, as I said, I believe that God created us so we can see the stars. So our vision is in that range that allows us to see through. Now, if we had vision in this range, we would almost see the sky as well. Not quite as well, because you can see it absorbs a little more. There would be a pro of having vision there. If we had vision in that range, we would be able to see in the dark. A con is we wouldn't be able to see things as clearly. Our resolution, the detail we can see, would not be as high. Why does that have less resolution? Because the resolution, this alpha, okay, that looks like not like an alpha. Alpha is the resolution angle. The smaller it is, the better. And it's like 0.02, I think it was arc seconds, multiplied by the wavelength in nanometers. So you just put the number of the wavelength in nanometers, divided by the diameter of the aperture. And so if you have a longer wavelength, you have a bigger size. That's the minimum you can resolve. How would an animal compensate for that? Well, you've seen those nocturnal animals. Many of them have a really big pupil. The big pupil is increasing the denominator to bring the resolution into better. So I suppose if we had big pan eyes, maybe that would work out okay for us. What was that? Then we have the radio window. Radio window would be wholly insufficient. I do have a picture comparing looking at Jupiter in radio waves to looking at Jupiter in visible light, and you'll see why that would be insufficient. But there are some other things to note for this. We will talk about this later when we talk about comparative planetology. But something that's kind of important in the public debate is talking about the greenhouse effect. So can somebody describe for the rest of the class what the greenhouse effect means?
The sun gives off its energy, then it gets trapped into the atmosphere. No, it bounces off the surface of the Earth, and then it gets released again. Then some of that gets trapped to the ozone layer.
Okay. He's on the right track. He's got a lot of the details in there. It's a lot more than most people know. Most people just, Earth gets hot. And it's bad. Most people think it's bad. There was a commercial I saw once for some company where they had people talking about their dream for the future. And one person, we can change our world so there is no greenhouse effect. Russell's laughing like an idiot. What would happen if we had no greenhouse effect? Yeah, we'd all be popsicles. That would be one way to assure destruction of life on Earth.
Too much greenhouse effect when we get like Venus.
Yes. Venus has a runaway greenhouse effect. It has too much greenhouse effect.
And Mars is the opposite.
And, okay. Here you go to teach the class. True story. My brother, when he was in high school, he was taking like a computer class, and he kept, saying things and teach Friday. Well, if you want to give a lecture, why don't you? So he came up and he gave a lecture. Yeah. She took notes and learned a lot from him. I'm sure it wasn't a quality lecture, but it was information packed.
See, I'm not much of a smart aleck where I would do that.
Yeah. My brother did a few things that impressed me. That was one.
That's so funny.
Okay, but obviously Russell knows his details here. We have a greenhouse effect that keeps the temperature habitable for us. If the greenhouse effect gets too much bigger, we roast. Too much smaller, we freeze. So let's just show how that greenhouse effect works, because this picture explains exactly what the greenhouse effect does. Okay, I've got to make another. I should have put this in already. Whoops. I got to put in another slide just so we can draw things and make pretty pictures. So here's our pretty slide. So what we have is the sun up here that Tioni spoke about, and the sun puts off light. What's the temperature of the sun?
Depends.
The temperature at the photosphere. Russell's feeling his oats now. The temperature of the photosphere, that is what we think of as the surface of the sun, the temperature where the light comes from that we see. You know what? It's about 5,800 kelvins. And that light comes and it hits the Earth. So here's our little green planet. And what's the temperature of the Earth?
Like 70 degrees.
Okay, around 70 degrees Fahrenheit. Let's just approximate that to about 300 kelvins. Between friends, that works. So what's going on with this greenhouse effect? The sun's radiation, if we use Wien's law, the peak wavelength that it's emitting is about 500 nanometers, right in the middle of the visible spectrum. And looking at this picture, that means the sun's radiation is right, the peak of its radiation is in that range that can go right through the Earth's atmosphere. So we have the sun's light, as Tioni said, coming in and hitting the Earth. Now that light, if you want to be honest, I don't know who wants to be honest, but if you want to be, some of that light is going to get reflected off of the atmosphere. And some of it comes on in. And some of that light that comes on in will get reflected out. But the amount that is absorbed by the Earth, that's the part that we're interested in for the greenhouse effect. The light that's absorbed from the Earth is then emitted at a much cooler temperature. What temperature? Well, we have 300 kelvins. So if we calculate the wavelength peak for the Earth emission I'm just going to round it off this time. We did it before. It was 973, I think. Let's just say, I think that's, okay. I think that was 1,000 nanometers. Does somebody have a calculator? Just do it real quick, just so I don't feel stupid. I don't want to be wrong. It's about 3 times 10 to the 6 divided by 3 times 10. It should be, no, it's got to have another zero. About 10,000 nanometers. Yeah. Okay, so this radiation that's coming off has a much longer wavelength. And here's the key thing. That longer wavelength, if you look in the picture, we're radiating in about that range. And in that range, our atmosphere absorbs the radiation. And then that radiation that's absorbed is heating up the atmosphere, and it's keeping that energy in the Earth instead of letting it escape. And so it's because of the shift in wavelength, because the Earth is not as hot as the sun, that it shifts from being in the visible range that can go through the atmosphere into an infrared range that can't get through the atmosphere. And so the greenhouse effect blocks some radiation from going out. The temperature increases until the Earth gets hot enough that the amount of radiation going out equals the amount of radiation coming in, on average. What was that?
Sometimes it gets so hot you can almost see it.
Sometimes it gets so hot you can
Almost see it.
almost see it. No, the Earth does not get that hot.
No. Like I've seen hot days and you can just like see it. Almost see the heat.
Actually, we'll talk about that aspect later on today. So that's what the greenhouse effect is. Now, since that's the greenhouse effect, we have to say what's causing the absorption in this block right here. Russell said CO2. For once, I can tell him he's wrong. Doesn't happen that often. Now,
It helps.
CO2 helps. What do you think is the most important, the biggest acting greenhouse gas? Methane is my number 2. What did you say next? Not nitrogen. What? Water. Latifah's on top of this. Water is the number 1 greenhouse gas. And carbon dioxide is a much, much lower greenhouse gas, much less effect than water vapor. Now, that being the case, why doesn't Al Gore talk about all of our water production from putting water into the atmosphere?
He doesn't know what he's talking about.
I'm not going to wax that political. There's actually a good logical reason that would not require us to malign anyone.
Could people just start the camera for water? That would happen.
Actually, you got a point there. That's not what I was looking for either. Because humans really don't affect the amount of water in the atmosphere. The temperature on Earth affects the amount of water in the atmosphere. When it gets hotter, there's actually going to be more water in the atmosphere. When it gets hotter, there's going to be more carbon dioxide in the atmosphere. In fact, historically, when they're trying to determine what the temperature on Earth was, one of the things they look at is how much carbon dioxide was trapped in the air. They find little bubbles that are trapped in ice. They measure how much carbon dioxide was in there, because the more carbon dioxide, the higher the temperature on Earth was. But basically, humans aren't affecting the water vapor in the air. And so that's why Al Gore doesn't talk about it, because we're worried about man's contribution to the greenhouse effect. And man's contribution isn't there with the water. But man's contribution is there with carbon dioxide. Now, what's producing methane?
Cows.
Cows. I don't know if you guys know this, but I went to Washington State University. Go Cougars. We finally won a game this weekend. And it was at Washington State University where the seminal research was done to measure how much methane was produced by cattle. They put little things there to measure how much came out when they belched, and other little things to measure how much came out the other side. That's my college. Yeah, very proud. But there's been careful research to measure methane production. Methane production comes largely from living things. So the fact that we raise cattle for beef is actually a much bigger contributor to greenhouse gases than the fact that we burn gasoline in our cars. But it's hard to get people on board with to stop eating beef.
Not happening.
Tony will second that one. So we go for what we can. Now, all of this said, I have to go on record. We will talk later about the Milankovitch hypothesis and the things that affect the global climate. Whether man is responsible for the temperature increases that have, in fact, occurred over the last 100 years or so, we still have a duty or responsibility to be good stewards of the earth. So I personally don't think we have enough evidence to know that man is responsible, but we still need to be careful to not be destroying the environment, even if we're not responsible directly for the climate. So we'll talk about that later, but I wanted to point out how this information plays into that debate. These absorption lines you see here are primarily absorption lines of water in the infrared, and that's what's causing the greenhouse effect. And as it gets hotter, you'll get more greenhouse effect because you'll have more water vapor. But there is another side to it. If you have more water vapor, you increase the Earth's albedo. The albedo is the reflectiveness. That water vapor reflects the light coming from the sun. And so as the Earth gets hotter, it will start reflecting more sunlight and let less in. And so there are some feedback mechanisms that, have kept the Earth. I mean, do you guys know how the Earth's temperature now compares to the Earth's temperature historically? We're a little bit below average temperature. We're still warming up from the last ice age. But, we'll get warmer, we'll get colder. We don't want to make it man's fault, though. Okay, so moving away from that, it's important just, to understand these things so you can be a little more intelligent in the debates, understanding what the greenhouse effect is, understanding what causes it, understanding carbon dioxide is a gas that produces absorption inside that box. Hence, it is a greenhouse gas. Okay, telescopes, where do we put them? If we can only use basically visible, small infrared range, and radio on Earth, we put them in orbit. Or put them on the moon. We have not done that.
It's a good idea.
So you see here different places that telescopes are placed, and you only see 2 telescopes shown on the surface of the Earth. One for visible light and one for radio waves. Do we have other telescopes? Sure. But those are the ones that it makes good sense to put them on Earth. Now, as we'll see in just a minute, it's not perfect to have them on Earth because of the atmosphere. In infrared, if you put an airplane up in the upper atmosphere, oh, that was beautiful. Let me undo that. Maybe. Change my tool. If you put an airplane up here in the upper atmosphere, you can get above most of the gases that are absorbing in the infrared, so you can make an infrared telescope there, or you could just have one orbiting. And I have a picture of the Spitzer Space Telescope that is an infrared telescope coming up. We have X-ray telescope, the Chandra telescope, named after, I can't pronounce it, I don't remember his first name, Chandrasekhar. That is an X-ray telescope that we can use. The Hubble Space Telescope is not shown here, and of course the James Webb Space Telescope is still in construction. Our first of 2 clicker questions. Oh, crud. Don't answer yet. Everybody got that? I don't know what happened, but reset. Good times. Okay, you can answer now. What ranges of electromagnetic radiation can easily pass through the Earth's atmosphere? And this is one where you answer all that you believe are correct and hit enter.
No, it's not.
My question's different.
It's not?
No, it's just like you have to pick one.
Your question is
It
different?
says, what
Yeah.
does resolution of a telescope mean?
I've got that.
That's
Oh,
what I
you're
have.
right. It does say that. Okay, that explains why.
My question says, what's the range of it?
Yeah. That's why things were going wrong. I opened the wrong file. Okay. It's too bad that this is recorded. Apparently the right file is not here. Pooh. That's what happens when you make them at home and transfer them. Okay, well, let's delete that slide, and we'll only answer one then. So now you can answer. And one of these 3 lucky students.
Am I on the list again?
No, you will be after the test.
Oh, Lord, why?
Oh, Lord, won't you buy me? Connor and Hannah. Thank you for pointing out that it was different, because I could see the questions asking you, but my brain. All right, everybody has answered. And here's what we had. 5 people said visible and ultraviolet. 4 people said radio and infrared. And one person said all of them. Now, Amelia. Ricewick.
I think radio, visible, ultraviolet. Because I mean, visible, ultraviolet for sure. And I felt like radio was too, but infrared I didn't think was.
So you picked all but infrared.
Yes.
Okay. And what were your reasonings on this?
Well, I mean, the thing you showed before, I talked about that, so starting from that. And also just, if you think about it, you get radio signal from, what are they called? I can't remember.
Radio stations?
No, but like, just, well, you know, ultraviolet goes through because we say you get rays from the sun. Visible, it has to go through the atmosphere for us to see it. And I just felt like radio did.
Okay. Good answers. Ultraviolet, you were wrong on. And let's talk about that just a little bit. Everybody has heard of the hole in the ozone layer, right? The what?
Isn't that over Antarctica?
Yeah.
Isn't that like well, also a lot of radiation just goes through naturally?
A lot of what?
Radiation just goes through naturally.
Sure.
In terms of like where the magnetic field isn't there.
The magnetic field causes charged particles to primarily go to the poles. When we get to that and talk about northern or southern lights, that relates to why that's where the hole in the ozone layer is. But the ozone itself is what I want to talk about. Ozone is a molecule that is made of 3 oxygen atoms in a ring. So ozone is like that. And ozone occurs naturally in our atmosphere. And one of the good things for us as humans about ozone is that ozone absorbs ultraviolet radiation. And so that ozone is absorbing the portions of the sun's emission that's in the ultraviolet range so that we don't have tons of ultraviolet light coming from the sun. We have a lot less because of that ozone acting as a filter. But of course, when the ozone absorbs the light, what happens is the ring gets broken. And so the ozone disappears. It's now oxygen that's been broken apart. And so for every time it absorbs the radiation, you have a little less ozone. And so during the summer months, which in the southern hemisphere would be our winter months, you have a lot more sunlight directly hitting the southern hemisphere. The Earth's magnetic field directs it so it comes in close to the poles, and you have enough ultraviolet radiation that it can get to the point where it essentially gets rid of the ozone in a region. And when it does, you get a lot more ultraviolet radiation coming through. And that ultraviolet radiation is not good for animals and humans. So ultraviolet should be blocked by that ozone. Why has the ozone actually formed holes recently? We believe it's because of pollutants such as the chlorofluorocarbons, things we used for refrigerants. We still do, actually. My AC leaks. Every year I have to spend like $100 to have a little more refrigerant put in. And in a year or so, it won't be available, the kind of refrigerant that we used to use, the Freon. But that gas, when it gets into the atmosphere, it breaks apart the ozone. And so that's why we're no longer allowed to use it as a refrigerant. It's a very effective refrigerant, but when it leaks, it does bad things to the atmosphere. So ultraviolet was blocked by ozone. Visible light gets through, radio light gets through. There is a small window for infrared. So infrared could have been an acceptable answer. It's generally not considered because there's a lot of absorption there as well, but there is a small window. So if I gave an open question like this, I would have to be open to people saying, oh, but there is that window in their answer. In which case, well, you have A, B, and C. A reminder about light pollution. This is a picture showing What you can see is where people live and where they don't. This is a picture of the United States at the nighttime. Yeah.
You can see like the eastern and western halves of like the U.S. power.
Yes, this here. Well, I'm in black. That's a perfect contrast color to this. There you have a clear divider between the old West and the new West. All of this out here would be the new West.
You mean the West?
Yes, I grew up on the West Coast, so I have my own. There's the far West.
Why are you going into
There's the
Mexico?
far East. Here's the Midwest, and here's the Mideast.
Why are
But
you going into Mexico?
what?
I didn't say nothing.
You see that?
Okay, well, let's stay on topic.
You see that really bright light at the other bottom of California? That's San Diego. That's where you should have put your line.
Yes. I was just making sweeping lines. I know the United States goes like something like that. But you can see the big cities. You can see the entire Los Angeles, Southland area there is lit up. Up here you see the North Bay and the South Bay there, San Francisco area. Big cities, obviously.
What's that really
a lot
bright
there.
light in the center, like in Texas?
I don't know. Probably Dallas right here, but I don't know.
I mean, more like one. Like
Actually, this here is more likely to be Dallas because Dallas should be a bigger city. I don't care about the cities' names right now. What I care about is we have a lot of light coming up from these cities. This is taken from above, so this is clearly light that's going up into the sky and going to be interfering with observation of things in the sky. And so that's a problem pretty much everywhere on Earth where you have people living except North Korea. Now, there are places where hardly anyone lives.
And Canada.
In Canada. Yes, he does point out you do have Canada there. Canada's boundary is down here. Everybody lives pretty much close to the United States and Canada. But hey, you have things like,
I mean, New York must be the best place to,
nobody lives in that thing.
That's because it's all radiated.
Okay. But light pollution, it's a real issue. And in places where we have lots of cities, like on the eastern half of the United States, you have a lot of light pollution. In places like Southern California, the California coast, huge amounts of light pollution, which makes it hard to do astronomy.
It's good to do it in that spot in Mexico.
It's also good to do it out here.
Because you can see Bermuda in there.
oh, that That's definitely Bermuda.
Yeah, it is.
Okay, so here is, I wanted to name this slide Twinkle, Twinkle, Little Star, but I decided that was just a little too
It's
juvenile.
copyrighted.
Might be. You guys do know that the copyright was lifted on Happy Birthday to You.
They finally did
You
it.
are now free. Yeah, it happened, 6 months ago. You are now free to sing Happy Birthday without anybody threatening to blackmail you or take money from you.
They released the copyright on Hong Kong.
Now, if only Disney released all their copyrights.
I really don't care about Mein Kampf.
You know what it means, right?
It's like my commander or something.
No, my struggle.
My what?
My struggle.
Struggle. Okay. My German is not so good. Okay, so Twinkle, Twinkle, Little Star. Twinkling of stars is a real thing. It's not imagined. When you look up at stars, they appear to twinkle. They appear to get brighter. They appear to get dimmer. They might appear to spread out in one way. And that's caused by real things. It's caused by pieces of atmosphere that have different temperatures. Because they have different temperatures, light travels through them at different speeds, and if it's not going straight into the surface, it will deviate. So the light does little deviations as it comes down. So when you look at a star, if it's just a point, and all stars except for the sun are just points as far as you can tell from Earth, even with the best telescopes, they're just points. And so if you're looking at just a point, those little deviations make it look fuzzy and make it look like it's moving around or getting brighter and dimmer, twinkling. Now, the technical name for twinkling is scintillation. And the name the astronomers give to the quality of your viewing is the seeing. So when the stars are twinkling, an astronomer says the seeing is not good because you can't see things clearly because of all of that twinkling. So what causes the twinkling? It's different temperature clouds up there. They're transparent. It's not like you have water droplets in them, but they're causing the light to deviate in path. If you can get uniform temperatures, you can avoid a lot of that. So for instance, there is an observatory that's built in the middle of a lake. You think lake, that's bad, a lot of water in the air. But water has a very high specific heat. That means you can put a lot of heat into it or take a lot of heat out and the temperature hardly changes. And so the temperature above the body of water is pretty uniform and helps to improve the seeing. So when you go out and look at the stars, notice, do the stars look like they're twinkling? Sometimes they'll look like they're twinkling more. That's bad seeing. Sometimes they won't look like they're twinkling at all. That's good seeing.
They never really twinkled back home.
Excuse me?
They never really twinkled back home.
I've never been back to Bermuda, so
You should. It's beautiful.
I probably should. You're right.
Hey, wait, oh, you've been there?
Yes, I have. I have family there.
Okay, so what causes scintillation or twinkling of stars? Okay, refraction from different temperature air. How do we deal with that?
Put it in space.
Okay, one answer is put it in space. You put it in space, you're outside of the atmosphere, twinkling's not a problem.
Now you just have to deal with the heat of the sun.
Well, yes. You don't point directly at the sun. That's one of the first rules of astronomy. Back in the late 90s, they called it the Guide Star program there at Lawrence Livermore National Laboratory. They developed a technique of, well, first of all, they realized if you look at a bright star, you can see how much the light is moving, and then if you want your telescope to focus on some faint object next to it, you just adjust the mirror of your telescope to stabilize the image. That is, because the light's moving around, it's not like image stabilization in your iPhone. Here, the light's moving around, and so you actually have to change the shape of the mirror to make it so the light comes to a point. They can do this with a computer. They'll make, like somewhere in the ballpark of 20 to 100 corrections per second to account for this variation.
Is that how they get like lasers to work in that atmosphere?
I'm getting to there. That picture shows a laser.
No, I mean not like that type of laser, but the really powerful ones that can burn through stuff.
No. Okay, but going with this guide star. So if you had a bright star next to a faint object you wanted to look at, you could use that. And then the people there at Lawrence Livermore said, but wouldn't it be nice if you have this faint star over here, there was nothing nearby that was bright, you could still focus on it? And then they came up with this grand idea. Let's make a laser that has the right energy of photons that when it gets into the upper atmosphere, it will be absorbed by the gases in the upper atmosphere. And excite those gases and have them give off a bright light. And so they make what looks like a bright star next to the faint star they're looking at, and then they can use the light from that man-made bright spot in the atmosphere to adjust for the atmosphere. And so that's what's showing in the picture on the left. They're using a laser
Can you actually see that?
to make a fake bright spot in the upper atmosphere so that they can then use their image stabilization.
Is that a visible light laser?
Um,
Or is there just artistic effect?
we were there during the daytime, so I didn't see it in action.
No, but like the one in the picture. Is that like,
Yeah, I don't think it's that dramatic if it's visible. So I don't know. I don't know what wavelength they're using. And so we call the changing of the mirror adaptive optics. And you can see here, this is non-adaptive. With the non-adaptive optics, that just looks like a bright spot getting dimmer as you move away. With the adaptive optics, you can see some definite structure to that object. This has got to be some kind of galaxy. So you can improve the resolution by about a factor of 10 by using these adaptive optics, which makes Earth-based telescopes a much better option than they were 15 odd years ago. Still better to get outside the Earth's atmosphere altogether. I'm not sure. Did you guys notice how many homework questions I gave you this week? Yeah, 4. Because we're winding down to a test. I don't remember if I put this in, but one of the questions I almost asked, I'm pretty sure I didn't, was about how long you have daylight if you're on the equator on the equinox. Now, on the equinox, if there was no atmosphere, if you're on the equator, you would have 12 hours of light, 12 hours of dark. But because of the Earth's atmosphere, that's not true. The Earth's atmosphere has a different speed of light than vacuum does. And the result, it goes slower in the Earth's atmosphere. So if we draw a picture of the Earth, and then we draw its atmosphere around it, if we have sunlight that's coming like this,
does it add like an hour or something to it?
Time I didn't even pay attention to. If we have light coming in like this arrow, is it going to bend toward the Earth when it hits the atmosphere or away from the Earth? Toward it. Why?
Gravity.
Not gravity.
Because like the angle of the gas doesn't like turn towards, like it turns with the angle.
Yes. It turns into it if you go into something slower. So what that means from a practical sense is that when the sun is on the horizon, it actually isn't. When it looks like it's on the horizon, it's actually below the horizon because the light's coming up and then bending in toward you. So we see the sun on the horizon about 5 degrees below where the true horizon is. So we actually can see, instead of seeing 180 degrees, we can see about 190 degrees worth of position of the sun because of that refraction. And so 190 degrees out of 360, that's more than 50%. And so we could do the calculations based on that, but I didn't. So when the sun sets, when the sun gets on the horizon is when you start having that effect. And so it will make the sun appear to change shape when it gets on the horizon because you have, it dropped down, but you still see the light there. So it kind of mushrooms out sideways and squashes down is what it looks like. So that's because of refraction caused by the Earth's atmosphere. Today's stuff is, I think, a whole lot of, gee, that's cool stuff, right? Okay. Thank you for appreciating what I appreciate, or at least nodding your head like you do. Okay, these are some pictures of some satellite telescopes. So you have the one everybody knows about, the Hubble Space Telescope here. And that's a visible light telescope. You have the Extreme Ultraviolet Explorer. Okay, I don't know that one. It doesn't have a cool name. And then we have the Spitzer Infrared Telescope and the Chandra X-ray Space Telescope. Different telescopes to look at different parts of the spectrum. Now I'm going to go through the telescopes again for why we use them because I didn't have the pictures I thought I had with them before. I don't know how. So the Visible Light Telescope, we really don't need to see a picture of it. It's historically the first type, although the first type wasn't made with a mirror. What do we call a telescope if it's made with a mirror? It's a reflector.
So that's a mirror type one?
Huh?
That's a reflector type?
That's a reflector, right? This is the opening out here.
Does it weigh less than like the regular lens?
So light is coming in. Back here you have your mirror, and yes, your mirror is going to weigh a lot less than an equivalent lens would. And so back here is your primary.
Does it cost less?
Mirror. Yes, it also costs less.
How much does it cost?
I don't know. This right there is the secondary mirror. And then it comes through a hole in the middle of the primary mirror and then out here to the eyepiece.
So another mirror.
Well, the eyepiece is a lens.
No, I'm talking about that.
Oh, yes, that's just changing the direction. But yeah, you don't have to have the wedge. It just makes it a lot easier to have the wedge so you can look on the side instead of having to look straight behind. So this here is the design that we call a Cassegrain. And actually, often you have at that opening a plate that does something special. It's called a Schmidt corrector to correct one of the optic problems. But that's your most common type of telescope that's used in research for visible light. And remember the magnification. Yes?
Does that telescope also work well when you're looking across the ground?
When you look in what?
When you're looking from high up and you're looking down at something? Can you use it?
You mean like, let's say I'm up at Glacier Point and I'm looking down at Yosemite Valley?
Yeah.
Yes, it would, but
Or would it be too powerful?
it would, well, you can always change the eyepiece to make it less powerful. But one of the big problems you would have is the fact that it inverts the image. So you see a car going this way, you have to turn the telescope that way to follow it because of it inverting the image. Magnification is minus the focal length of the objective over focal length of the eyepiece for the telescope. And in this case, while the length of the light path is equal to the sum of the focal lengths, the light path doubles, so the actual length of the telescope is half of that length. And so here's some pretty pictures of visible light. Ooh, pretty. Sombrero, which I'm trying to learn Spanish, and I learned it just means hat. You know, we always think sombrero is a special hat. No.
Yeah, Latin words like the sent from Latin have that type of flavor.
And then over here, the Hourglass Nebula. Now, this here is a super cool nebula from a star that has had a supernova. And so you have in the center here a pulsar. Actually, wait. No, it's not supernova. This is a white dwarf that collapsed to a white dwarf. That's a white dwarf. White dwarf in the center. And you have the cloud that used to be gas or used to be part of the star out there. So this is what we call planetary nebula.
A supernova that creates like a black hole, right?
A supernova either creates a black hole or a pulsar. Pulsar/neutron star.
So
Either way.
There's really no difference between like a neutron star and a pulsar.
Well, we'll talk about those later. I think he asked, does everybody know the difference? The only difference between a pulsar and neutron star is a pulsar is a fast rotating neutron star with a strong magnetic field.
Does the neutron star spin?
If it does, it's called a pulsar. Okay, radio telescopes. We've already talked about the size, 305 meters across for this Arecibo telescope. A key thing that I talked about that they look at is that 21 centimeter spin flip radiation. That's where the magnetic moment of the electron switches from being aligned to anti-aligned with the nucleus. You can observe them through clouds at day or night. Here's a beautiful picture of Jupiter. The lower one's visible light, the upper one is with a radio telescope.
It looks like one of those spaceships from like Space Invaders.
I would say that it looks like a spaceship from Star Wars.
Nah, you mean the
I
TIE
mean, a
fighter?
potato is a spaceship.
Yeah,
Okay, but what do you see in that thing with the radio waves that you simply can't see with visible light? The ring around it.
The TIE
Right.
fighter.
Now, there is a ring of debris around it, but unlike the rings around Saturn, there's a ring around all of the gas giants. But the rings around all of them but Saturn are gunky black stuff that's really tiny, like sand-sized particles. And you really can only see them if you have light from behind shining through them. This here is actually showing gas that is orbiting around Jupiter. So it's not showing the physical ring that we think of as a ring, but it's showing gas that's going around Jupiter. So you see entirely different things about Jupiter with the radio wave telescope that you do with the visible. And so you can get a fuller picture of what's going on by utilizing these different wavelength pictures. Infrared telescopes view cool gas and dust. 10 kelvins, very, very cold. 500 kelvins, pretty warm by you and my standard, right? We would burn. And once again, they can penetrate clouds. And so here's some pictures of infrared images. Beautiful colors, right? Do you remember what I said about those colors?
Artistic license.
Yeah, artistic license. They're not real colors. So the colors represent what the person who made the picture wants them to represent. So The
Like isn't each color like supposed to be a different gas?
It depends. It depends on what they want to do. The one on the right is including multiple ranges, and the colors represent different wavelength ranges. So the one on the left, you have very short infrared. The one on the right, you're going from short to long infrared. And you can see these are all looking at the same place. And you see here in the shorter infrared, a lot of detail. Here you see in the mid-range infrared, a lot of gas. And then here it's put together so you can see the detail is pinkish and the gas is greenish. So they put the information together using different colors so you can see different parts of the detail in one picture. So these are all pictures of the same Eagle Nebula taken by the Spitzer Space Telescope. Then X-ray telescopes for super hot things. And so here's an X-ray telescope image, and I put the key on this one for what each color represents. And you'll see that the colors actually represent not just different things, but different types of things. So the red and yellow are telling you about what atoms are present. The red is oxygen atoms, the yellow is iron atoms. But the blue is telling you about the motion. That's telling you where things are moving outward. And so you have the colors put together to give the data that the person wanted to see from this. But what you're seeing here is an explosion with super high energy. Okay, the last thing before the test, amateur astronomy. Does anyone here own a telescope? One person. You what? Okay, when you're buying a telescope, you know, why do you get one? Well, because you want to look at the sky. It's kind of fun to look at the sky. My only drawback on that is, of course, it happens at nighttime when I like to be in bed. So binoculars are a good way to start. Of course, quality binoculars are also going to cost you some money. A digital telescope with a telescope mount is great. That is, if you have a telescope that you can control with a little controller, it's going to make life a lot easier. Because it's really hard to aim those things. I have a dickens of a time getting my controller lined up to get started. So one of the things that I like to look for is the ability to have a computer-controlled telescope. Now, of course, that costs you money. A second thing to consider is if it has a CCD chip. If you're looking through an eyepiece versus the CCD chip. Because if it's using a CCD chip, you look at it on your computer, you control it on your computer, you capture pictures on your computer, you do everything on your computer. It's really convenient. But of course, those cost you money. Most of us are probably not going to make our first telescope one that has all of those toys with it. I was going to take this out, put it in, take it out. I couldn't make up my mind. We have rods and cones. I already talked about the cones, 3 types of cones, blue, green, and red. Hence, those are the 3 primary colors of light because that's what we basically see. Our brain puts together colors by just saying how much of this type of cone was activated, how much of this, and how much of this. So I know I have some people here who are into graphic design. And if you are choosing a color on the computer, you just say, okay, make it simple, 0 to 255 red, 0 to 255 blue, 0 to 255 green. You choose a number for each one. If you're making a web page, you specify that by something like, 00FF93.
That's good.
Yeah. The 00 is 0 for the first color. FF is 255 the second. 93 is, 9 times 16 plus 3 for the third color. And so you're specifying how much of each color you want. And our brain just does the reverse. Our brain says this much of this much of this much of this. It's magenta. And so our brain is just interpreting how much of those were activated, which brings up some really interesting physiological things. You can have 2 colors that look exactly the same. They're actually made up of different wavelengths because you can get the same amount of activation for each kind of cone with different amounts of this light and this light. So it's really a complicated system. If you ever go somewhere like the Exploratory Science Museum, one of the cool things they have is 2 colors that look exactly the same. They give you a color filter that blocks a certain color. you pass it over, and the colors look extremely different because they weren't the same. It's just our brain interpreted them the same. Something that's really, really curious. First of all, you probably know if you have somebody who's colorblind, they're almost certainly a male. Color blindness is a I think it's sex-linked trait that dominates, or it's a dominant thing in men and recessive in women or something like that. There are some women who are tetrachromats. Most of us are trichromats, blue, green, and red. Some women are tetrachromats. They actually have 4 different kinds of cones. Each cone basically gives you about 100 variations that it can detect. So our normal vision, 100 for each cone, we have about 1 million colors we can see. That's what we consider the color gamut for the human eye. But for one of these ladies that's a tetrachromat, multiply that by 100, and you have 100 million colors you can see. It's pretty amazing, right? And so I've read articles about, like, a lady says, I look at these 2 colors, and everybody says they look exactly the same. And to me, they're not even close. And, she was an interior designer, she has this advantage, although I'm not sure how much advantage it is if nobody else can see the color variations that you do. But I think it would be awesome to have that going on.
There's a shrimp that has like 16.
I do not know this. When you're out observing, you want to get used to seeing in the dark. It takes about 20 minutes for your eyes to adjust. That's the biggest reason why, well, that and the fact that the weather hasn't been clear yet, we've been meeting and having lectures in here to start off the lab periods. Now, we're still going to meet here, but if it's clear tomorrow night, I'm not going to lecture. We're going to immediately go out. If it's not clear, well, yeah, then I'll do an activity. I probably still won't lecture. But it takes about 20 minutes to get used to the dark. Also, it's not really dark at sunset. You have to wait about an hour after sunset. So right now, sunset is like at 7:30-ish. So by the time we get out there, if it's 8:30, it's probably dark enough we'll be able to see the sky. It takes about 20 minutes to get used to the dark, and it takes only a few seconds to lose it.
So, Dr.
Yeah.
I noticed something the other night. Saturday night, the moon was full.
Mm-hmm.
So
Actually,
that might be on.
Yeah, well, now it's waning. So that means it doesn't rise until after sunset. We'll be good. One last thing. This is a list of things to think about when you're buying a telescope, if you're thinking about buying a telescope. A good starting size is somewhere 4 to 6 inches. If you can afford it, get bigger. But that's a reasonable size to see a fairly faint object. With a 10 centimeter telescope, you can see cool things like the rings of Saturn. Messier catalog we'll talk about later is a list of cool objects that you can see. Refractors are excellent. Reflectors are more affordable and better. So I would go for a reflector because it's generally going to be cheaper. You get more for your money. Don't forget eyepieces and mounts are important. And I don't even have that question ready.